So this video is on nucleosynthesis, which is section 2.7 in your chemistry textbook. And I've entitled it, Where Did It All Come From? So I want to look at this question. So this is a deep field image from the Hubble telescope. So you're looking out at lots and lots of galaxies. So each galaxy, is filled, fair teeming with stars and planets. And so we might ask, well, how did this all get here? And that's a question that's been asked by humans, over the centuries, and many disciplines, many different ideas of humankind have answered that question. And so what I'm going to tell you about is what we think the modern scientific answer is to that question. And it's the Big Bang Theory. So you read about this back in Chapter 1. And so this is a little model timeline for where everything came from. So you'll recall from Chapter 1 that there's evidence that all the stars and all the galaxies are moving away from each other. So if you run time backwards, we have to assume then that they were all once much closer together. In fact, the assumption is that they were once all packed together in a dense ball of energy that began at a single point where all space and all time began, and that's called the Big Bang. So if all this energy were initially spread out in the whole universe, if the whole universe expanded from this one point, then the leftover heat from that big explosion should more or less be uniformly spread out through space, although there's a theory that said it might be have some certain patterns to it. But in any case, what we've discovered is that yes, indeed, there is a little bit of residual energy that seems relatively constant wherever you look in any direction in space. And furthermore, those little patterns that I told you about, they seem consistent with this idea too. So that's further confirmation that this Big Bang idea might be the correct notion. In any case, according to this theory, very early on after the Big Bang, there were only elementary particles. So this is 10 to the minus 10th second. So that's 10 billionths of a second after the Big Bang. There was this soup of elementary particles. So all we had were electrons and little tiny particles called quarks. Now as the universe expanded, that energy was able to spread out, and so things cooled down. So it didn't cool down much. It's still scathingly hot here. But those quarks were able to get together and form the particles that we now know as protons and neutrons. And then there were lots of electrons buzzing around as well. So at that point, we're in a region that we call Primordial Nucleosynthesis. And so we're going to learn about how early elements were made, because in about 1,000th of a second after the Big Bang, we start to see hydrogen and helium nuclei around. So initially the early universe, mostly hydrogen and helium. And in fact, as the universe has continued to expand, it is still mostly hydrogen and helium. So that kind of corroborates our idea about this Big Bang, that early on we could form these guys, and they're still mostly what populates in terms of elements our universe. So let's step over to the chalkboard and take a chalkboard, my digital chalkboard, and we'll take a look at how primordial nucleosynthesis happens. So nucleosynthesis is just the name that chemists and physicists use for the process by which particles fuse together to make the nuclei of different atoms. So we're going to talk first about primordial nucleosynthesis. So in the Big Bang picture, we're about 4 minutes after the Big Bang, and the universe has expanded, and it's still really, really hot though, so about 1 billion degrees Kelvin. So in this hot, dense sort of soup, this primordial soup of particles, remember we've got protons, neutrons, and electrons. So it's gotten cool enough that those quarks can get together, and 3 of them can combine to make these things that we call protons. Now we need to think about some other processes that can happen. So this process is called fusion. And fusion just means that we've got the nuclei of atoms, so things like protons and neutrons, well, they come together and they stick together to make a bigger glob. Alright, so that process is called fusion. So this is the nucleus of one atom, the nucleus of another atom, and they come together and fuse to make one bigger nucleus. The opposite process is called fission. Write that down over here, fission, F-I-S-S-I-O-N. And so fission is when a bigger nucleus decays into smaller particles, like 2 smaller nuclei. So breaks apart somehow, and maybe gives off other kinds of particles or other kinds of energy like light. So that might happen as well. So in this case, we're going to look at what we've got in our soup. So what can happen is a proton can come together. So nuclear chemists, nuclear scientists represent a proton with P there for our symbol, and then just like we did with nuclide symbols, we're going to represent the mass number. So a proton has a mass of about 1 in atomic mass units. And then down here we're going to write another subscript, that's the charge. So this is the charge. A proton has a charge of +1. And so let's say in this hot primordial soup that a proton and a neutron collide together really, really hard. So a neutron has a mass number also of 1 and a charge of 0 though, right? So we're going to represent this happening by saying a plus sign here. So this is like a reaction. So this plus this yields or produces something new. So the way we're writing things here, remember this is the mass number. So let me write that up here, mass number. So mass number, that's supposed to be a pound sign. And this down here is charge. Okay, so there's an important principle that you need to apply when you're writing equations like this. So we need to conserve both mass and charge. So conserve means that the total on one side has to equal the total on the other side. So it can't be created or destroyed. So if we add up all the mass over here, we've got 1 plus 1, that equals 2. So over here on this side, we're going to have a new particle that's caused by fusion that now has a mass of 2. So we're going to put a 2 as a superscript up there. I'm going to leave this symbol here for a minute. And the other thing that we have to conserve is charge. So when we add up the total charges here, we have to get the same total charge over here on this side. So 1 plus 0 is 1. So what we're going to get is a new thing that has a charge of 1 but a mass of 2. So this thing we actually recognize it is this nucleus. So this is an isotope of hydrogen, right? So it's got 2 particles in the nucleus, 1 proton and 1 neutron. So this is an isotope of common hydrogen. And this isotope is called deuterium. So deuterium is what you get when you have a hydrogen. Now we'd have to have an electron to actually make this deuterium. So sometimes a nuclear chemist will call this a deuteron and represent it by the symbol D. So 2 plus 1. So this would be a deuteron. That's just a deuterium nucleus. So the nucleus of a deuterium atom. So we spell it kind of like deuterium, and then we end it with the on. You know, like protons, neutrons, they always end in the on. So deuteron. So that's the symbol for a deuteron. And so this is going to happen, you know, kind of a lot in the primordial soup. So we have a lot of high energy collisions, we fuse them together, and we make these deuterons. So what can happen next? Well, again, if we've made enough of these deuterons, they might collide. So we have one deuteron right here. It's going to collide with another deuteron right here. So we're going to write that plus sign here, and that yields, after the collision, a new particle. Now we've got to conserve mass, so 2 plus 2 is 4, so we fuse these guys together, and we've got to conserve charge, so charge is going to be 2. So we've got something that has a mass of 2 and a charge of 2, plus 2. So what can have 2 plus charges? Well, helium, right? So helium has an atomic number of 2 because it has 2 protons in the nucleus. So this is helium-2. So we've made helium now. So we started out with hydrogen, we made this isotope of hydrogen, and now in the primordial soup we can also make helium. By the way, there's another name for this. This is sometimes called an alpha particle. So it's given the symbol alpha. That's the Greek letter alpha. It looks kind of like a little fish. That's the lowercase letter. And a 4 and a 2 right there. So the nucleus of a helium atom is called an alpha particle. Alright, that's supposed to be a T and that's supposed to be an I. There we go, an alpha particle. Okay, so that's what's going on in the primordial soup. So at the same time, the universe is continuing to expand. Now, if there had been enough energy, these alpha particles could have collided, and in fact they probably did. Unfortunately, what they form is then not stable, so they make something that then instantly breaks apart. So in order for these guys to collide, we have to have something else that happens later. And in fact, the universe got kind of too cool for this to happen. So we assume that science predicts that after a little while in the universe, we pretty much had a soup of deuteriums, hydrogens, and helium nuclei, and that was pretty much it. So we had to wait for some other event to happen because the universe got too cool to continue to sustain fusion, and we could no longer fuse these alpha particles to make heavier elements. So in the next part of this video, we'll see what happens inside stars to make other kinds of particles. So now the universe has continued to expand. No longer is primordial nucleosynthesis sustained, so now we've got this soup of atoms. So now we have to wait for a really long time. Perhaps it was as long as 1 billion years. But then finally, the universe, gravitational attraction was able to pull those atoms of hydrogen and helium together into big clouds of gas, and eventually those clouds of gas began to compress under their own weight, and under those tremendous pressures, those atoms picked up enough energy to start fusion again. And once that started, it released even more energy, and we got this fireball, the birth of stars. So about 1 billion years ago, we imagine, according to the theory, that stars were formed. So inside really, really massive stars called red giants, then we can have other interesting processes that start taking place. So in this case, we're going to imagine that we have 3 alpha particles that can come together at the same time. So here's one alpha particle. Remember, an alpha particle from the last part of our video is just the nucleus of a helium atom. So hydrogen is still being fused into helium in stars. That's mostly what gives the sun, our star, its light, is the fusion of hydrogen into helium. But deep in the core of supermassive stars, other things can happen. Now, this would be a pretty rare event. You'd have to have 3 particles coming together at the same time. But there's such tremendous pressure there, and these heavier particles might sink towards the center under gravitational attraction anyway, so there's a chance that this could happen. This is called a triple alpha process. Because it involves the coming together of these 3 alpha particles. So these 3 alpha particles collide, again, really high pressures, really high temperatures, and what do we get? Well, let's think about it. So we're going to fuse these 3 particles together. So we're going to add up these numbers here, 4 plus 4 plus 4, that gives us 12. So we have to conserve mass, the top number, the mass number, and we have to conserve charge, the bottom superscript here. So plus 2, plus 2, plus 2, that gives us something that's going to have a charge of plus 6. And what do you have that has 6 protons making up its nucleus? Well, looking at the periodic table, we see, oh, that's carbon. So we've just made carbon from helium. So this process produces carbon. Now we've got a stable isotope. So I told you that just 2 alpha particles colliding would give us something that would have atomic number of 4. So atomic number 4 would be beryllium. Unfortunately, the mass number is too big, and that isotope of beryllium isn't stable, so it would fall apart. But now we've made something that is stable. So now we can continue this nucleosynthesis process inside stars and really make a whole bunch of other elements. So imagine now we take one of these carbons. So here's a carbon 12, and now it's going to fuse again with, say, another alpha particle. So these things are going to smash into each other. What do we get? Well, remember, conserve mass. 12 plus 4 is 16. 6 plus 2 is 8. What has 8 protons? An oxygen atom. So we've just made oxygen. So again, stars are this nursery, this cradle for all of these elements that get produced. And so we can continue on colliding different particles together, making elements, up until the point that we get to iron. So it turns out that iron is sort of the peak of stability. So, so when we make iron 56, this isotope of iron, which has 26 protons in it, at that point, any other fusion that we do, so as the iron begins to be made, it sinks towards the center of the star because it's heavier. It will continue to collide with other things. Unfortunately, all these other collisions that we've been talking about also release a tremendous amount of energy. So that's where stars, produce all their heat and light and other kinds of processes. But once we get to iron, the star is in trouble. It means the star is starting to run out of fuel. Now iron will continue to fuse with other things, but unfortunately now what's going to happen is that process is going to take energy. So we can still continue to make all the other elements on the periodic table inside stars, but now we're starting to consume some of the energy of the star. And so now the star is going to cool off. What happens when it cools off? Well, those outer layers that are held out by the intense heat and pressure are going to start collapsing, and the star is going to sort of crush itself. And as that happens, even more heat and pressure will be generated inside, and there'll be more fusion and lots of interesting things, but the star will continue to lose energy, and eventually it will die. And if it's a big enough star, it dies in a really spectacular way, something called a supernova. So let's think about processes that can happen now inside the star. So this is called neutron capture and beta decay. So we'll write that down, neutron capture and beta decay. You might be curious about this little funny symbol that I wrote here. That's the lowercase Greek letter beta, B-E-T-A, and so this is called beta decay, and we're going to use this Greek letter as a symbol for a particle, just like we used alpha as a symbol for a kind of particle. So what happens now? Let's imagine we have an iron nucleus somewhere inside this star. So here's an iron nucleus somewhere inside the star. So this is a mass number 56 and has 26 protons in it. So in this case, we're going to let this iron collide with 3 neutrons. So this iron nucleus is going to collide with 3 neutrons. So there's 1 neutron, 2 neutrons, 3 neutrons. So these neutrons are going to be captured by this iron particle. And what do we make? Well, we make this guy. So we haven't changed the charge, so it's still iron. We still have 26 protons, right? Because 26 plus 0 plus 0 plus 0 is still 26. But now we've got 56, 57, 58, 59 as its mass number. And it turns out that that kind of mass makes the nucleus unstable. So it's going to fall apart and decay into other stuff. And so this is the beta decay part. So neutron capture happens first, and then we get beta decay. So let's scroll down here a little bit, give ourselves some more space to write. So now here's the beta decay process. So we've got this iron nucleus that's now unstable. So what is it going to do? Well, it's radioactive, so it's going to radiate some of that energy off. It's going to cast off some energy, and in this case, a particle. So what is it going to give off? Well, it's going to give off a particle that we call a beta particle. So I'm going to write that right here. So here's the beta particle. Now beta particles are really, really light. It turns out that compared to 1, they're about 2,000 times lighter than that. So 1/2000th of this mass up here. So we're just going to call that 0. And beta particles have a charge of -1. And in fact, beta particles are something that we've seen. Beta particles are just electrons. So this iron nucleus has produced something with a negative charge, an electron, that we call this beta particle. So electrons, beta particles, same thing, different words for the same thing. So now we need to figure out, well, what's the other thing that's produced? All right, so let's go back and remember we have to conserve mass. So 59. So 0 plus what is 59? Well, that's easy. So we still have 59. So now we have to figure out, well, what is the subscript number? So 26. That has to equal what we add to -1 to get 26. So what can you add to -1 and get 26? Well, that would be 27, because 27 minus 1 is 26. So now we can go to our periodic table and look up, well, what has 27 protons in the nucleus? So isn't this interesting? We had 26 protons, and now we've created something with 27 protons. Well, that element is cobalt. Alright, so we've produced cobalt now, which is a heavier element than iron. And so this is an example of how we can produce other heavy elements inside stars by this process of neutron capture and beta decay. Okay, so the last bit. So we've got this big star here, and it's got all these layers inside of it where all these different elements are being created. And down here is the iron core. Now this supermassive star, as I said, begins to lose energy, and as it does, it begins to collapse. Once it reaches a certain critical point, it's built up so much pressure and run out of fuel that what happens? Well, it explodes. So there's this tremendous boom when you have a supernova like this. can't hear it in space because there's no atoms to transmit sound. But anyway, there's this massive explosion. So the star explodes. It's called a supernova. And that tremendous nova, not novae, so nova, and that tremendous explosion is going to take all these elements that have been made and cast them out, spread them far and wide. And then eventually those little bits will come back together, and they're going to form, and the gas is released, other gases will come back in, will form new stars, and perhaps from the other bits, planets. So that's what we suppose happened here in our solar system, that these bits of residue from the explosion of a supergiant star, that those bits came together and then produced our sun, a second generation star, and the planets that surround us. So we are all stars, in a manner of speaking, or at least children of stars, because all the elements that make up you and me and everything else that we interact with were formed in the cores of these supergiant stars under tremendous action and activity. And I think that's pretty neat and impressive, don't you?